Hey everyone, today we are going to graph the square root of a messy looking quartic polynomial. And although it looks horrific at first glance, once we start simplifying it down and looking at its factors, we'll see that it's a more manageable task than it might look at first. So let's start with the rational root theorem to consider the possible roots of our quartic polynomial. Now, we know that any possible roots of this quartic are going to be factors of 18 over potentially factors of 2. Those candidates are what? Positive or negative 1, 2, 3, 6, 9, and 18 over positive or negative 2. Let's make our lives as easy as it can be. Let's start with the easiest candidates first, i.e. let's start by testing x is equal to 1. And testing x equals to 1, plugging it into the quartic and seeing if it evaluates to a value of 0, meaning it would be a root, an x-intercept. We plug in x equals 1, and we get 2 times 1 to the power of 4 minus 16 times 1 cubed plus 44 times 1 squared minus 48 times 1 plus 18. And that is 2 minus 16 plus 44 minus 48 plus 18, right? We know that when we plug in a 1 in for the x value, we can just look at the coefficients, right? Because 1 to the power of anything is 1. And so 2 minus 16, that's negative 14, plus 44 is 30. 30 minus 48 is negative 18, plus 18 is, in fact, 0. And so we get a factor of x minus 1 to start things off. And so that means that we can now write f of x as f of x is now the square root of x minus 1 times some cubic quotient, right? So to find this resulting cubic function, let's divide using synthetic division, let's say, by the factor of x minus 1, meaning that we have a root at 1, and so synthetic division, our coefficients are 2, negative 16, 44, negative 48, and 18, 2, negative 14, negative 14, 30, 30, 30, negative 18, and 0. And so we have this cubic polynomial as our first quotient. Since this is our first quotient, and we will have more, I'm going to call this q sub 1 of x, i.e. the first quotient of our polynomial f of x as we find all of its linear factors. And so you'll notice that these terms are all multiples of 2. And so I'm actually going to factor out a factor of 2, and I'll throw it at the beginning, and then I'll reduce that, or I'll simplify it rather. I'll simplify that cubic with the 2 factored out of every term to x cubed minus 7x squared plus 15x minus 9 to make our lives a bit easier numerically. Now, again, this 2 should be at the very front because it's factored out of the entire quartic. So we continue by trying to find the next linear factor of this cubic. Let's test 1 again. Maybe we'll have a double root. So if we try 1 again, x is equal to 1 means that plugging into the cubic, we get 1 cubed minus 7 times 1 squared plus 15 times 1 minus 9. That's a 15. And that is 1 minus 7 plus 15 minus 9, and that is 0. And so x minus 1 is a factor again, let's say. Again. And so now we can therefore write f of x. Let's contrast colors here. We can write f of x as now the square root of 2 times x minus 1 squared, right? Since we have the factor of x minus 1 twice, it's at least a factor with a multiplicity of 2, i.e. at least a double root. And then we'll have the second quotient, right? Again, that's why I labeled this the first quotient, q1 of x. And now let's divide this cubic by another factor of x minus 1. see what quadratic comes out of it. So again, the root is at +1. The factors were the coefficients rather. The coefficients of the cubic were 1, -7, 15, and -9. And so synthetic division, this will be our second quotient as a function of x. I'll call that q sub 2 of x, q2 of x. And that is x squared minus 6x plus 9. And this might ring a bell when you see that quadratic coming out of our quartic polynomial. This, you might notice, if you've factored out these, is a nice perfect square. This is x minus 3 as a binomial squared, meaning that f of x can therefore be written as the square root of 2 times x minus 1 squared, being a double root at +1, times x minus 3 squared. Now, what this means is that we have a double root at 1 and a double root at 3 in the quartic polynomial that is found underneath this square root. So let's graph the quartic. Let's graph just the quartic as a dashed blue curve. Okay, let's sketch it at least. So we would have a double root at +1 and at +3. Let's use a different color. So it really pops out of the board. 1 and 3. A double root at both of those. And this is a positive quartic. And so we're going Q2 to Q1, staying high to high. Our y-intercept would be at +18. That's somewhere way up there. And so it would look something like that. That would be our quartic, right? Very roughly speaking, we would have a y-intercept over here at 0 and 18, right? A double root at x is 1, a double root at x is 3, and it would look something like that. Now, you might be tempted to say, well, since f of x is the square root of a couple of squared factors, can't we simply cancel the square root with the squares? And although it might be tempting to do that, if we did do that, if we wrote this as f of x is equal to √2 times x minus 1 times x minus 3, if we did make the square root cancel out the squares on the two factors, this would be the result. This would be a quadratic parabola with a vertical stretch of √2, roughly 1.4, roots at 1 and 3, and it's a positive leading coefficient. So we would have a parabola that starts high, goes through the root at 1. It would dip underneath the x-axis, right? It would have a vertex at +2 between the two roots. And so that would make it dip below the x-axis into the negative y-coordinates, and then it would pop back up, right? So it would look a lot like this, but it would go into the negatives, right? When we're taking the square root of factors that are squared, these squared factors are always going to provide us with positive values. Any squared factor, any squared value is positive, or at least not negative. It's at least 0. And so that means that we are taking the square root of numbers that are never, ever negative. So our square root function is never going to go below that x-axis, right? It's never going to have any negative y-coordinates. And so we can't simply cancel out the square factors with the square root, because this parabola that would look something like this does have negative y-coordinates. This does dip into the negative y values. And that's not what we're going to see in the behavior of our actual f of x curve. If we take the square root of this, it's going to look something like we'll have invariant points where y is equal to 0 and where y is equal to 1, right? We can make our best estimations, something like this. Okay. We know that our y-intercept would be at the square root of 18, right? I'll remind you that root 18 is root 9 times root 2, and that's 3 root 2, which is roughly 4.2, let's say. So we'd have a y-intercept somewhere around here. And then we're taking the square root of a quartic, right? So this is roughly, very roughly, going to look like the square root of an x to the 4, which should be an x squared. And so, meaning that when we actually try to sketch the f of x curve, we know we have a y-intercept at 0 root 18. We know we have invariant points where y is equal to 1 and where y is equal to 0. And so our square root curve is going to look something like, we know that below the value of y is equal to 1 and above y is equal to 0, between y being 0 and 1, the square root of a number is bigger than the number itself, and so that should be reflected. That should be something like this, something like that, a curvy, and then from here on out, this should look something like that. A bit tricky to graph, but it should hook above it between 0 and 1, and then we know it grabs this y-intercept. And then, again, we're taking the square root of a quartic now, so this is still going to rise fairly rapidly. This should be symmetrical. This, again, is proving a bit tricky to sketch with any kind of precision, but it would look something like that. Quartics grow very, very fast, right? As the x values diverge from the roots, the quartic functions rise super fast. And so the square root of it would still rise reasonably fast, right? Akin to something like a quadratic function. And again, the concept that I really wanted to hone in on is that we can't simply take the square root of the squared factors and cancel them out, because that would give us a quadratic, which would dip into the negatives between the two roots at its vertex, right? And the square root of a quartic simply does not do that, okay? And so this is our very rough looking sketch. This is my analysis of the process of sketching this curve, and I hope this helps. Thanks for watching, and thank you so much for all of you that have been supporting my channel for the better part of the last 3 years. We just hit 1,000 subscribers. I am so grateful, and thanks again. Take care.